Okay, good afternoon, everyone. So, I think I'm going to take off the mask. So, I wanted to spend some time today uh, showing you a few of the projects from last time. What I also did just before the class actually is on Piazza, I have put in links for the final presentation part of last fall's projects. Okay, so now just bear in mind they are pretty uneven in quality, so do look at several just to kind of get some calibration. But I'm going to walk through a few of them just to describe what the students did, and I'm going to just go down the sequence. So they may not be the best ones, but I'll just tell you my perceptions of those. So if you don't mind, I'm going to sit down because what I'm realizing is the screen font is a little bit too small for my eyes. So okay, so firstly, just to walk you through what you should be doing. So firstly, you should be meeting me. There's office hours today, or just set up a time with me to bounce project ideas out. There was one student who has done so thus far. I was hoping more would have by now. So you would be submitting. Ideally, you'll meet with me as a team if you have figured that out, and bounce around ideas, and then as once we have reached an agreement, sometimes students come up with the same ideas that kind of veer them away. You are going to create a GitHub repo. So if you see this particular project, the very first one, so these guys have GitHub repo, and what I do is I give a template for the GitHub repo. So you just copy that template and then sort of you fill it out to organize the code and all in a fixed manner so that I have an easier time looking through it. And also as part of it, you will have a GitHub pages to do it. Now what these guys did, so let me also open up their final presentation. So red light, green light. Remember that? How many of you have watched this? Okay, great. Yeah. So basically, these guys, it's a great example of, right? I mean, the gun shooting. You have to detect the person moving. There is a lot of sensing and actuation and real-time constraints involved. So this was a group of 3 students who were all UCLA undergrads and had just started as master students. So they were pretty gung ho about it. I let them do it. This was actually one of the best projects in the class. I think it brought in computer vision, controlling a motor, sensing movement. There's a lot of cool stuff in a single project. Certainly worthy of a team of 3. And did they meet all the goals? There were some snags, I mean, in terms of latency and all, but they did pretty well. I think I gave all of them A pluses. I think the combination of effort and quality was pretty good. Okay, so last time we were still kind of in this quasi-pandemic mode, so a lot of stuff was happening. I mean, we had in lectures, but a lot of stuff was still in the pandemic era. So what I did was the presentation was through a YouTube video, which every student made. I think part of it was just a scaling issue. So every team had a YouTube presentation. I think there was a time limit I had given of 18 minutes, if I recall. So these guys kind of did that. So kind of you. Okay, so I'm not. Okay, so it's a usual. You make slides, you make a presentation. So each team had to do a final presentation demo. So these guys actually had as part of it, kind of they showed off the demo. We also had every student do a midpoint presentation. Again, I give a structure, so I kind of say you need to have these slides. The midterm presentation is pretty short. I think I'd given like 7 minutes or 5 minutes or something like that. So let me just open this one up. Okay, so the midterm presentation, I just asked for what the goals and specific aims are. Like, I mean, kind of like a overall vision and kind of just very specifically what you are doing, what would you deliver, I guess, if you may. Slide on the technical approach. So as you can see in the video feed played, as you kind of decompose it, particularly if you're in a team project. Talk a little bit about the current status, data set, and it varies from project to project, obviously, and then the next steps. So that's the midterm part, and then for the final presentation, it's a little bit more freeform, but still you kind of build upon this. Okay, so that was project number 1. Oh, let me also show you the report. So that's the GitHub repo. So in the GitHub repo, you attach kind of content for GitHub pages. Hopefully some of you have heard of it. Those of you haven't, basically in GitHub repo you can have either a folder or a I guess branch in which you can put the content. Okay, so again, I kind of provide some high level guidance on this thing, but you can kind of look what they have. There's a part where kind of all the required submission and so on and so forth. Okay, anyways, so that's project number 1. Let's look at project number 2. So project number 2, super resolution with pixel subsampling, and I think this continues to be kind of a area where interesting projects can be done. So this basically has to do with sampling of signals, okay, and I'm sure at least those of you who are electrical engineers, you have heard of Nyquist sampling, right? I mean, we talked about a couple of I think 2 lectures ago, that we have to sample at twice the maximum frequency component of a signal. There are few things there, which is one is our goal in that case is to reconstruct the signal. So right, I mean, if you sample at that thing, then in theory, I mean, if you do the thing correctly, then you would be able to perfectly reconstruct the signal by taking those samples. So what's happening with the standard Nyquist sampling is that our goal is to perfectly reconstruct, and all we exploit about the signal is that what is its maximum frequency component, right? The knowledge about the signal is limited to that, and our goal is, like I said, reconstruct. Both of these are relaxable, right? I mean, oftentimes I know something more about the signal structure, like for example, I may know it's not just a microphone signal, but it's actually human speech, right, for example. Or maybe the reconstruction is not the goal, maybe I just want to know is the speaker male or female, for example, okay, or maybe I'm detecting for the word whatever, okay Google, okay, or something like that, right? I mean, your favorite sort of wake word. So my goal may be limited, and I may have more knowledge about the signal. And so over the past couple of decades, along this line, people have been doing smarter and smarter ways of sampling things. So this one, you probably have seen some versions of it, that how do we take an image, that's spatial sampling, and how can we create a higher resolution image out of it, right? Now the naive way of doing it would be simply replicate the pixel, perhaps do some smoothing on top of it, but you can be a lot more clever, and particularly if you look at modern phones, I think Google in particular has been pushing this quite a bit on the Android side of things, where what is the content of the image could be exploited, things like that. So in any case, super resolution refers to getting more resolution than what you had sampled with, okay? And these guys kind of explored some methods. This is where some of the work in deep neural networks using generative so-called GANs and all have been used. So these two students kind of explored that. Using these kind of ideas, there are papers which are showing that, you know, you do sub-Nyquist sampling, but if you know it is human speech, then you can still recover it. Namely, you can unalias the signal. Okay, aliasing happened, but you can undo the aliasing, for example. So if this is a space any of you wish to explore, I can certainly point you to some papers and ideas. I think the image stuff is pretty done in the sense, and hard to compete with. I mean, it's very data intensive and hard to compete with what Google and all, Apple, Google are kind of doing, but perhaps looking at some other kind of signals like in motion sensor data or speech data or some such thing, or radar data, those would be interesting to explore. Okay, let's look at the third one. Ashwin Narkar, yeah, I remember him. So, spatial radio source detection using SDR. SDR stands for software defined radios, which are basically, you can think of them as antenna with a RF front end and then a very high rate A to D converter. And essentially what radios do, now you can do in software, you write a program to process these things. And now you bring to bear kind of all the power of software processing. What used to be done fixed in hardware, now you can essentially write code to do it. So it, in recent, starting around 90s when the trend started, but I think now you can, on Amazon, you go and you can find sub $100 SDRs, and you can do pretty cool stuff with it. Now, of course, transmitting any sort of radio signal in most cases, unless you are in the right band, is illegal, right? You don't want FCC to come after it. But even otherwise, you can do a lot of stuff. What this project was about was he was using SDRs from a lab, and he was trying to find radio sources and classify their modulation scheme in the process. I think this project, the student tried, but the project didn't turn out that well. But I think a lot of it had to do with just the background of the student. He's a CS student, so and getting into some physical layer kind of thing. So, but I think it's a great space to be in. It was motivated by work that happened in my lab by one of my current PhD students, and which was the following. I'm sure you may have heard about these things, like, you know, how you check into an Airbnb and the host is spying on you through a hidden camera or some sort of thing. So the goal of my student, Akash, his project was finding hidden sensors which are hidden behind wall or inside walls, and essentially being able to look at their radio signals and then see whether they're actually spying at you. Very crudely speaking, what Akash was doing was he would have the person in the room, like if you're a person, you move and the phone on you is using your motion sensor to see how you are moving, and then it looks for traffic. Now in his case, he was focusing on cameras and all, cameras and microphones which are Wi-Fi. So he would look at the Wi-Fi traffic, and the idea is you establish a correlation between the two. You don't have to decode the packet, but the amount of packet. Like if I'm moving, whenever I move, there's a burst of packets. Whenever I stop, there are no packets. So you begin to look for correlation between your movement, which you can measure through the phone in pocket, for example, and the camera. And likewise, I mean, there's some other ideas that he did. So this was kind of motivated in that way, in where like we wanted to identify hidden things and all. Okay, so again, this is I think there's a lot of cool stuff can be done, and particularly SDRs are, like I said, they're like sub $100 SDRs also, which do a lot of interesting bands. Okay, as long as the project doesn't involve transmission in what are called as transmission outside what are called as ISM bands. ISM bands are the bands in which your Wi-Fi operates, or some of these devices. There you can transmit relatively freely, but elsewhere you can't. So this projects like these, you have to make sure that you're using the right bands and all, but very interesting space to work in. You essentially are hacking the airwaves in some senses. So if you have never worked with SDRs, I think it's a cool class of projects to get. Okay, let's move to the next one. So what did these guys do? Simple Hope appliance monitoring. Okay, so what these guys were trying to do was to use that tiny Arduino devices and all, and to look at what appliances are coming on off. So there has been this line of work where people are interested in human activity in homes and what appliances are coming on off. Sometimes it has to do with like what is a person doing and all. Sometimes it has to do with sustainability goals, like for example, if I know whole house energy consumption from the meter, and then if I hear the microwave sound, then I know at that time microwave is on, and then kind of attribute energy accordingly. So disaggregating energy consumption, assigning it to the right appliance. So there's been a lot of interest in identifying appliance usage, and these guys were doing it. Main thing was that they were trying to do it on a tiny little device out here, these Arduino class stuff. So the sampling of the signal, I think they were relying on sound primarily, and the classification and all, because you can't just stream these things continually. So they were running the classifier locally and things like that. So the project brought together those kind of ideas. Okay, let's see. So that was 4, 5. Central server based smart camera system. I don't recall what this was. I need a smart camera home. Okay, yeah. So there's this line of work which is that where should you do processing of sensor data, right? And particularly as we have moved towards kind of more accurate deep neural network type stuff. So what's happening is that you can stream the data onto a central server and run kind of like a big heavy duty model, which would probably be more accurate, may generalize better to conditions that hadn't seen at the training time, and therefore may be more robust to deployment. But then you are sending a lot of data out, right? Versus you can do something right at the edge, perhaps with a simpler model, which would be less accurate, less robust. Since you have a tinier processor, maybe latency may be more also. So there are trade-offs between this edge cloud kind of a thing. So this project, and I think there were a few other projects which were kind of dancing around this theme of how do we look at whole pipeline, like from I have a camera or microphone or whatnot, and I need some inference, or maybe even I'm closing some sort of a control loop, and how do I spread it between an edge device and a central device. So there are all sort of approaches you could do it. I forgot precisely how the student was doing it, but like, I mean, there are ideas like, you know, I'll make a inference locally, or maybe even just look at some features locally at the edge, and only if there is something interesting happening, or maybe I'm doubtful about what I am inferring, then I go to the back end and employ, refer to the expert model which is running at the back end. I recall there was another project which was along the lines that I have the model running on the edge, but occasionally I will cross check it and see how it was doing against what the expert model is doing. And if I see that the model at the edge, the tiny model, has begun to perform badly, perhaps because maybe the environment is different, or maybe the world has changed or whatnot, then I would send a new model or retrain the model, adjust the model. So I think this theme of looking at the overall pipeline between the edge and the cloud, I think there's some interesting opportunities there. The ability to run models, train models, and run models on server class machines obviously is very, very robust. Many of you perhaps would have seen it in some other courses perhaps, but it has also become pretty mature on tinier devices, and it goes under the broad name of EdgeML and TinyML. These are kind of the names referred to it, but they're very robust pipelines and that can work with. So again, an interesting area to work with. One experience I guess I had with these projects was that working with cameras on the tinier devices tends to run into just data collection. I think the implementation issues are kind of come in the way. So you have to kind of be you should be comfortable with programming in the low-end devices. A lot of time things like interfacing just to the sensor, grabbing an image, getting it out. Some of these things just take some getting used to. So it's not as simple as working on your laptop and all. Anyway, so that's what this project was doing. Let's try the next one. Yeah, so what this project was doing was, so one of the problems that continues to be kind of a topic of research at some level is finding precisely location in indoors. So like, and there are two challenges out here. Firstly, when you are indoors, you don't have access to like GPS and all, but more importantly, indoor applications often tend to require location at a finer level of accuracy, centimeters or millimeters, whereas outdoor the applications tend to be more about like vehicles and pedestrian movements and all, whereas indoor they tend to be more about let's say guiding a visually challenged person or things like that. So what this project was exploring was localization using RF signals, and I think this project had a couple of different dimensions to it, but that's what loosely speaking they were exploring. So that's why the name localization, but they were exploring that. I think exploring locationing and locationing in a broad sense, so like absolute location in space, relative location between things, location and orientation, these are all pretty interesting, and many facets of these things are open, and there continues to be lots of new technologies coming. So again, if the space interests you, talk to me. I can suggest some possible directions to have. So what we have seen thus far is then edge AI split, locationing. You saw a couple of application-oriented things. We saw an SDR. Let's see. This one, automation of home lighting with learned BLE positioning. So home automation type projects, a lot of students like doing, and there are a lot of interesting opportunities possibly there. Some of you perhaps have home automation devices of some form at home. What this guy was trying to do was have the automation be done where after the system observed that the user, so let me back up. So many home automation systems allow you to have rules in there, right? Like for example, whenever the front door open, turn on whatever the light in the entryway. But these are hard coded by the users. You kind of go into the system, anticipate these rules, kind of write these things down. What the student was trying to do was that by observing patterns from the sensory data, can we learn the rules and then the system adapts. So like for example, I just buy the system, install it at home, and it observes that, you know, every time the front door opens, seconds later the light in the foyer turns on. So that becomes a rule, and then the system, so it's kind of like a good butler who sort of observes and begins to anticipate your need. That was the goal, and part of it was knowing therefore the location and stuff like that. So he was using BLE. It was a small scale fun project. He was doing it alone. But there are lots of interesting possibilities in this domain, and also particularly when you combine with, like, I think there's some cool project ideas could be around, like, you know, now that systems like GPT-3 and all allow you to have very nice natural language interfaces. So there could be some interesting projects, and you could also look at more complex behaviors as opposed to simply I enter and turn the light on. Maybe something like when I have retired for the day, then do something. So more complicated behaviors by looking at data from motion sensors, BLE, and such. Anyway, so that was this project. Let's see, next one. By the way, all the presentations you have access to from BLE enable HID based on edge inference accelerated handwriting recognition. So let me see, there were a couple of projects. Yeah, okay. So what this project was basically trying to do was, on an edge device, essentially it was creating a touchpad where I can write letters, and it would recognize the letters. So essentially you have a n by n touch screen, and you are writing with your finger, and the system in real time with very low latency has to identify what letter you did. It's a little bit like, I don't know if any of you have ever been in a BMW, so its control is like that. You kind of with a finger right thing. I think some other cars may have that too. The thing out here was that trying to do it again on this little platform. So there were a lot of interesting challenges and optimizations that come into play as to the recognizing the letter itself. If you have done a machine learning course, a very standard thing is MNIST, where you recognize the digits. So letters are not too far off. So these guys collected a lot of data, trained it, did a real-time implementation on these things, and had a lot of fun. There were a lot of interesting issues along the way. So I guess at some level you could argue that this one didn't push. I mean, I can. Like I said, BMW has it, so clearly they do something like this. On the other hand, this was a good project in the sense it brought together a lot of interesting elements, and in the course of the project, they kind of learned a lot. And also the other thing is, I don't think BMW does it on a tiny little device like this. I mean, they send the signal to the whole big nav unit, so there was still kind of an interesting element out here. Okay, it was again one of the top projects in the class. Let's see, this one, Wi-Fi sensing with ESP32. Yeah, this was so this project was done by the student, PhD student in CS. So it related to some work he was already doing as part of his PhD thesis, and this relates to that. Let's say you have a Wi-Fi. Let's say your mobile phone is Wi-Fi. Can I use it? Can I use this interaction with the access points which exist in the space around you to help it localize? So the issue out here is the following: that like let's say in this building, there are obviously lots of Wi-Fi access points and labs and CSNet runs and campus runs and all, but they're not necessarily cooperating with you. You can't just like, unless you have the right account and all, you can't register with it. What this guy had done was he had figured out some vulnerability in the Wi-Fi protocol, which allows that if you send a particular type of packet, then the base station responds in a very deterministic manner, and therefore he was using that information to get the distance from nearby access points, and then using that information to then kind of do localization and some other things. So it turns out there's a body of work in recent times which shows that you can, if you measure the wireless signal at a pretty low level, then you can also extract things like heart rate and respiration rate and get location of as it showed. So he was basically kind of making a project around that. One of the interesting thing is he was using ESP32, which are those tiny few dollar type devices, literally like $3-4 you can buy them. So that was part of the interesting part of the project, kind of doing it in a very resource constrained setting also. So yeah, so this was a good project, rather well done. Again, I guess as an area, exploring radio signals as a sensing modality previously I talked about SDRs, radio signals as a communication thing, with, and looking at software-defined radios, but also projects which explore radio signals to sense the state of the world around, and particularly now that you have Wi-Fi built into tiny devices, so you need to have an interface to the radio, which is not simply give me the packet. You need a interface which tells you something about the radio signal strength and different frequencies, and then you can use that together with machine learning algorithms to do some interesting stuff. Okay, so that was one more project. Sorry for swamping you. I'm just want to give you a very high level thing. I think really encourage you to on your own go through the one. If any, I couldn't figure out very easily to give access, or well, maybe I was lazy, so I don't have YouTube links and all. If some project really appeals to you and you really want to watch the YouTube thing, just send me a note on Piazza and I'll put them up. Yeah, I think this project is again in the same vein of inference split across a resource constrained edge device and a resource rich central server. I think one project which would be cool to explore is, so thus far, I mean at least last year, a lot of these projects were simply about capturing some sensor data and I have to make an inference and I'm just looking at just latency. But doing something where you go beyond that to where you actually close the loop. So oftentimes what happens is I capture some sensor data and I have to take some action based upon it. There's a control. And now I can do the control, close the loop locally, or I go all the way to the cloud and come back. And if you go all the way to the cloud, maybe your accuracy is better because you have a better model, but then you are paying the hit of going to the cloud device. Now, that used to be a very simple proposition because I do it locally, I have a poorer model and slower device. Okay, so those contribute to a poorer performance of your controller. I go to the cloud, I have a better controller, better model, but I'm going to the cloud, which when data centers are few, so oftentimes it could be, let's say I'm sending it to something half the country away, maybe it's 20, 30, 40 millisecond round trip, and that can have significant implications. But now cloud services have gotten a lot richer, and you can place computation in what are called as edge servers, which are closer to you. Okay, like they may be at your ISP right here in LA, or maybe the base station in your cellular provider. It's all at some appropriate cost and things. So like companies like Amazon and Microsoft and all, they all have this kind of rich offerings. So one of the questions which becomes is, how do you place the computation? And the answer to that is not that straightforward because it may depend upon where you are, what your connectivity is, if you are on a slow link versus a 5G link versus a Wi-Fi link. So just examining some of these issues of edge cloud distribution of computation in a setting where either things are dynamic or the result ultimately needs to come back, right? I mean, let's say I'm running a car which has a camera and it needs to be controlled. Should it be done locally? Should I go all the way up and benefit from the richer resources? So I think there are interesting possible projects there. I do have access to one or two cars which like Amazon is called Deep Racer, which is a car with camera and controllability and all. So I can support like a project or two around these themes. Okay, let's see, next one. Yeah, this was a nice project. The results didn't turn out to be that great, but okay. So the issue out here is the following. If you have a microphone and you are capturing sound, there may be multiple sound sources or multiple people speaking, right? How can we separate them, right? I mean, so if you are, let's say, running a appliance recognizer like one of the earlier project had, or speech recognizer, right? I mean, so you want to separate them out. So how do we normally do it? Let's say multiple people were speaking, you want to separate out their sounds, how might you do it? Any thoughts? Any of you have, let's say, whatever, Amazon Echo or one of your digital assistants? How do they work? Like, how are their microphone systems organized?
You have to train.
Huh?
You have to train it on your own speed.
No. That is to recognize who it is. But how does it focus on your sound and not extraneous?
Bandpass filter?
No, that will do just frequency. Yeah.
It's like a keyword. Just,
Keyword is to wake it up.
Different direction?
Huh?
Can it have different direction?
Yeah. So how does it get different direction?
Maybe they have more than one microphone.
Right. They have a microphone array, 5 or 7. So basically, what they have is they have like an array of microphones, and then there is a signal processing technique called beamforming, which essentially what it does is imagine. Let's say, for example, let's say these two tables were the two microphones, okay? And if a sound source was somewhere in the back wall and right in the center line, then the two signals will arrive at the two microphones simultaneously, right? Because they're equidistant. But if the microphone was in one far corner, that far corner, let's say, so it will arrive at the gray table later and the brown table first. And if these two were tightly synchronized and processed together, then we can begin to say which direction they are coming from. So if you have multiple microphones, you could figure out the direction. More importantly, then you can cause the microphone to focus in that direction, as in you can cause it to amplify the signal in one direction and suppress in the other direction. This is a technique used in radios. Nowadays, if you buy Wi-Fi access points in recent times, they have many antennas, the same purpose, right? So they are able to increase the range by doing this beamforming, or what is often referred to as MIMO, multiple input, multiple output. So that's the class of technique. So you can have an array of receivers together with some fancy signal processing around it. So that's one approach. And you could argue that we as humans do a little bit like that also, right? We have 2 ears, we have a sense of the direction and all. But we go to parties and a lot of people referring, and if I have a familiar voice, then my brain latches onto it, right? I mean, it's not relying, and actually you can try the experiment. I mean, you can shut off whatever one ear, you'll still be able to do it. So clearly something else goes on out there, right? It is happening at a cognitive level, so to say, right? At the processing inside the brain, as opposed to relying on brute force of having multiple sensors. So with deep neural networks, now work has emerged which shows that you give a sound stream which has multiplexed speakers, and then you can separate them out. So like I've seen some work from Facebook which kind of can separate out up to 4 or 5 speakers like that, right? I mean, so you could, this again goes to the issue of like, sometimes you solve problems by brute force, almost like hardware approach, if you may, and sometimes you solve it by exploiting information at a higher level. So I'd suggested this project to these guys because I'd seen that Facebook paper and it seemed kind of cute, because you can now have a single microphone, and then with an appropriately trained model you can separate things out, separate audio sources. So that's what I had these guys look into, and moreover do it on an Arduino. Okay, I mean, so not like, Facebook obviously does it on big servers and all. So that was the project. Okay, so the issue out here is you kind of separate, and then you have to see how much, like your goal is one sound source separated into, let's say we place a limit. Let's say we say I'm going to allow up to 3, so you kind of separate out 3. The results were kind of mixed. I mean, it did some separation, but not that great. Actually, one of the undergrads in my lab has used some other type of models. They're not just neural models, and has pretty good results now. So, but then he uses much bigger thing. Anyway, so that was the idea behind this project, separating sound sources. Okay, in general, the problem of separating multiple sources
is a common problem with sensors, right? Lots of sensors pick up multiple objects, multiple targets, multiple sound sources, right? I mean, multiple signal sources. So separating signal sources from a single stream is the problem, and you could either cheat by saying if my sources are spatially separate, then I can have multiple receivers and then they will get a different view of the target. So that would be like the microphone array solution. Or I could go after some semantics of the thing, of the signal, and some well-trained model to separate things out. Okay, so again, interesting area for exploring some additional project ideas. So this was a good project, even though results were not that great. Thing I would highlight again is that picking an interesting top problem, and even if the answer doesn't come out to be that great, that's fine. I mean, it's trying and exploring systematically, which is the important issue. These guys did do that part. So very systematically done project. The results are what they are. It's possible that maybe, I mean, it's you can never prove the negative. So I don't know whether these guys like whether a solution doesn't exist, but they did do a reasonable go at it. Okay. So that was next one. Smart auto feeder with remote control. Yeah, this was just a cute little project. They were very, I think one of the students in the team, she had a cat and she wanted to create a smart auto feeder for the cat, which would had both water and whatever, the meal for the cat, and involve like when is it full or not, stuff like this. There was a mix of sensors and stuff like that brought in together. It was a well done thing. They also had a mechanical component to it because they had to design kind of a whole package. So this was one of the projects which occasionally happens in the course where there is also a mechanical component and not just electrical and computational. Okay, so it was a good project, but like I said, application oriented. So this project did a little bit of something I was talking a few minutes ago, which is if I have a low level control like motor control or something, and so normally, so how do we control motors, right? And we sense the position of the motor and then control the voltage or whatever, and we use control algorithms like PID control and all. But if you look at kind of more complicated control scenarios, then the controller tends to be more let's say you're controlling a robot or something, then it could be a more sophisticated control. So oftentimes these systems are now being done where control is being implemented as a service out in the cloud. So let me explain. Nowadays you can go to AWS or Google or Azure and get ML as a service, machine learning as a service. I have data, I want some inference, I can stream my data to that service in the cloud and get back a result. And not just these three, there are other services, right? I mean, I can send an image and have it return the objects in the image. So there are companies that provide these services. What has begun to happen is something similar along the lines of control, which is ultimately when we have data and we make inferences from it, it is for some purpose, which is I'm then going to control something. So there are control as a service, and some rudimentary versions for home automation and all have been around, but now we are beginning to see that, for example, companies providing control as a service to like factories and things like that. Okay, so essentially you can offload sort of high rate sophisticated control there. You could imagine that a service may control swarms of autonomous vehicle or drones or things like that, so that instead of these things. So this project was kind of exploring what is the impact when you have a control loop spread across the edge device, whatever that stuff at the edge, and some server under network dynamics where bandwidth is changing and stuff like that. So that was kind of the idea. It was kind of motivated by something which again is kind of, I think, is a space for interesting projects, which I guess is one of my wish list to make happen. So I'm sure all of you have seen those robots which are on the campus to deliver food, right? Okay, so what happens? They can travel on the campus, if appropriate. They can even sort of call for help and all, but essentially they are outdoorsy things, right? They come to the front of your building and then you go there, and I've never used them, but I imagine there must be some sort of a app code, whatever, opens the thing, you pick up your package or something. Okay. Why can't they not come inside the building and deliver it right in front of my office door? So how can we make that happen? Now, if you think about that, right, I mean, a package delivery robot which can navigate not just outdoors but also through buildings and all, there are challenges, right? I mean, our buildings are designed for humans. How will the robot call the elevator? How will the robot open some door? Stuff like that. Okay, so kind of, and so that's one part. The other part is buildings already have some sensors and all, right? I mean, so could they assist the robot, right? I mean, so that it doesn't go into areas it's not authorized to, and perhaps it can navigate and sort of things a little bit more easily. So I guess the project idea that I've been sort of is that how can we have buildings and robots cooperate? And you can take it as buildings and robots, or robot, like you can imagine a drone coming in and then it has to safely land on the building or even fly inside the building. So in future, as urban robotics, tinier robots roaming around and all come into play, I think somehow they have to interact with the infrastructure. So some project exploring in a tinier, more controlled setting, a robot interacting with a new environment and then doing some of these things, right? I mean, we clearly with smart home technologies we do have ability to open doors and stuff like that and all, but it's a question of having things interact. Or another thing, our homes often have compute resources. Can a visiting robot make use of those resources? So we are beginning to see some early stages of this notion that as devices roam, they can make use of communication and computing resources that exist in their immediate surrounding, even if not owned by the user. So there are two examples that currently exist. Amazon has this thing called Sidewalk Network, which I think I might have mentioned in one of earlier courses, earlier lectures, where as you go around your neighborhood, if they also have these Ring devices and all, then a certain amount of bandwidth can be used by your device to maintain connectivity. Okay, so essentially they're creating a neighborhood network. I've also seen some company which advertises something similar, some similar capability using Wi-Fi access points. Apple, for their AirTag, has this Find My network, and so even so, as long as you put an AirTag, let's say you put an AirTag in your suitcase at the airport, it still tells you the location even though you are not near it, and the AirTag only has short-range radios. And the way it is doing is, it's every iPhone essentially acts as a base station, okay, unless you explicitly disable, but then you also lose the service. So like you can see whether your suitcase actually got loaded into the plane or not, for example, or where in the airport it is. And so these are examples where third-party devices, their capabilities are being used in an appropriately safe manner and all. But why stop there? If I am visiting, if the robot is visiting Boulter Hall, why not make use of some compute resources or sensors and stuff like that in that? So that's kind of the notion. Okay, so anyway, I think this project, while that was my like high level pitch, this project kind of looked at a very specific aspect of it. Okay. Let's see. Project number 14. Obstacle avoidance system for the visually impaired. This was actually a cool project. I guess my eyesight is pretty bad, so I kind of relate to any technology which helps with visually and other sort of physical impairments. So I guess I have this attracted me from that perspective. So what they were trying to do was helping visually challenged or blind people navigate the world. And I guess pre-tech days, sort of the stick that the blind people use, right? The white stick, right? And you kind of probe the world with that, or guide dogs are the other. But with emergence of sensors, and there are lots of efforts on kind of bringing technology to this at various scale, navigating the outside world, helping them get onto, let's say, a train or a bus. Like, I mean, even little things which we take for granted, which is where is the bus door and all, I mean, can be very challenging if you don't have that. Or just going around, right? I mean, sort of navigating, let's say, the sidewalk on campus, particularly with all those scooters and all on pedestrian walkway, which are a challenge even for the sighted, let alone for those who are not sighted. So anyway, this project was exploring how a suite of sensors, I think they were using a combination of cameras and some sensors on body, would give essentially a situational awareness of around the blind person, and then translate that information into something that they can understand. Now, of course, vision is not an option, so usually when conveying information to visually challenged people, haptics and sound become an option, right? Sound by appropriate modulation of frequency and relative strength on the two ear, and likewise haptic. I think these guys were using haptics, I forgot, but anyway, combination of these two can still convey information about what type of object it is, where is it coming from, like which direction, how far it is. Some of these things can be brought in. Even for sighted people, something like this can be useful, because if you are distracted, so I've seen some projects from other places where, like, I mean, you're crossing a sidewalk and you don't see a car coming in, and also just sort of alerting you on that front. So this project basically was that. I think it's a great space to be in. You could also imagine, like, other places where people have challenges, right? I mean, again, visually challenged people in a new space, like you check into a hotel room and all, just guiding them through there. So that requires a more finer level of things. So I think there, just generally around the theme of accessibility, there can be some pretty cool possibilities. So anyway, so that was a project here. I forgot what this one was. I'm going to skip this one. I think it was again exploring virtual numeric keyboard. Let me make sure that I yeah. So what these guys were doing was, so there has been a line of work from various places which essentially says that, how can we make richer interaction with our wearable devices? Now, challenge is that, I mean, they're tiny and all, so our usual keyboard and all don't exist. So, and also the thing, so anyway, that's kind of the idea. How do we interact with computing which is on body or just built in without access to usual big keyboards, and where perhaps speaking is not an option? So if you look at your, like, smart watches and all, I mean, there are tiny little keyboards on the thing, but that often people find clumsy and they're limiting, right? I mean, like, my Apple Watch kind of shows me numeric stuff and all, and even that can be a thing. So there has been line of this work where through gestures of various forms can be engaged. So that has been a body of work. But then what people have also begun to do is create keyboards out of nowhere. So, like, for example, what if I write the number 2 in the air? Can you detect that? or can I use my knuckles as a form of keyboard, right? I mean, kind of simple typing surface, or can I use place a piece of paper and type on this thing out here? So essentially, can I create simple keyboards or other interaction modalities? So what this project was doing was, it was basically kind of seeking to do that. So you kind of tap, and it's just a numeric keyboard, but it's on any arbitrary surface that you create. Okay, so you do an initial calibration. This is a 0, this is a 3, and then at that point you kind of type. Okay, there are many other versions of it. There's a project I've been engaged in where we kind of use these our knuckles. Okay, so like make that as a surface. And in our case, what we do is we type out here. We have a variable, and the vibrations that as we type are picked up by the variable, and then we are able to do it. I've also seen work where kind of people do various actions like this, and then the twitching action is picked up by the variable. So anyway, that was the idea out here. Movement being picked up to create this kind of a virtual keyboard. I think generally speaking, there's some interesting possibilities out here. You can also imagine in many cases we rely on signals. Like for example, if you have ever seen like police going into in a movie, if you have hopefully have never done it in person, but in a movie you have seen a SWAT team going inside a thing, or military, right? They often hand signal with each other, right? Or bikers and all, right? They hand signal to each other. Visually impaired people rely on the sign language and all, right? I mean, so there are many places where we have visual communication through which is happening through gestures. Technology can perhaps come in play in those kind of settings. Anyways, so that's what this project did. And last but hopefully not the least, energy efficient cross camera communication to classify overlapping field of view. Okay, so what this project was seeking to do was the following. So again, the theme at a high level was, how can I make inferences from resource constrained edge devices? But what they were exploring was the following, that there is a large scene and there are multiple cameras, and instead of all the cameras monitoring and continually analyzing the scene all the time, if they were to cooperate, perhaps things could be more interestingly done. So like for example, let's say there are 2 rooms. When the person is leaving one room, then the camera in this room can signal the camera in the room where the person is headed to, and then it wakes up and starts. So this is about mutual coordination to wake up sensors, so that collectively we maximize their sleeping time and also minimize the processing overhead on the back end. So in this case, there are the idea was an overlapping field of view, so the camera's field of view are partially overlapping, and then kind of you're coordinating across them. So in general, cross-sensor coordination is kind of a theme, and this project sort of is in that territory. Okay, so these were projects from last year. I'll similarly try to put the links to the, I think the year before that was not, the course was in shambles, honestly, because of the pandemic, so it changed, I mean, that one year. But before that, things were, projects were, so I think 2020 wasn't that great, 2019 and earlier. So I'm going to put links to those, but don't spend time too much, because I think if you go too far back, then the technology has changed and the problem sets have changed, so it will probably not be terribly useful. I think last year's project are probably sufficient for you to look at. Now, come and talk with me, and I think I just like to listen to your interest and background and then suggest things. Okay, I think that's what I've discovered works very well. So team up among yourself, if you have friends in the class and all, and then let's talk. Okay, so we are kind of at the hour point, so let's take our 5-minute break. I know you may not need the break, but I do. Been speaking for an hour, and then we start on the main lecture.
Okay, let's. So, one student asked. So, in terms of meeting me, of course, office hours, but I have only 1 hour of in-person office hour and then 1 hour of virtual office hour. But you can always write to me on Piazza, and then we can find a time to talk on Zoom. Usually, in general, early mornings and late evenings work the best for me in terms of free time. During daytime, there are often other meetings, but sometimes that can also work out. So when you write to me, suggest some time, but not just a time. Suggest a few times. Okay, so we can converge on something. Weekends are fine too. Yeah. One other thing, just I'll take this opportunity to mention. I'll also send a note on Piazza. Next week, so there are a few days I'm traveling this quarter, but thanks to Zoom, we don't have any missed lectures, I guess, at least not. So next week, both the lectures, Tuesday and Thursday, are going to be on Zoom, as in really Zoom. So don't come here, just join on Zoom. After that, I expect there to be, I think, one in November, which would be like that. Yeah, I'm anticipating at least one more. Maybe there might be one more like that. Also, I think October 28th, I think. No, October 27th, Thursday. That lecture, it's in person, but it would be a guest speaker from ST Microelectronics, which is one of the big companies that make sensors and microcontrollers and all. So it's one of their research leads who's going to be giving a talk on sensors and microcontrollers and all. And I think there's some interesting stuff to say. So I thought it would be good for you to have a industry speaker. So just wanted to alert you to that. So if things go as planned, we won't have any missed lecture, but just some lectures may be virtual. Okay, so last time we were and by the way, I mean, hopefully virtual is not a problem for anyone, but in case it is, I'll also obviously record them. So okay, so last time we were just talking about how simulations and emulations play a very important role, and that how the programming of embedded devices kind of takes a looks. Okay, so so when it comes to programming these devices and all, I think one comment I had made was a typical cycle is that you develop on a different computer and then you download to it. Although certain kind of devices like Raspberry Pi and all, which are kind of the high end, you could certainly run compiler on the device too, but it's not something which is very commonly done. When you are looking into 8-bit class devices and also 32-bit devices which are not capable of running general purpose operating systems, is almost always kind of a cross compilation type toolchain. Now, when it comes to so in this cross compilation setup, simulation plays a very important role, and there are a wide variety of processors. So fortunately for us, there is a software framework called QEMU, which is very cool piece of open source software which can emulate a variety of processors, 8-bit, 16-bit, 32-bit, and actually without you explicitly knowing it, you might even have used it. If you have ever developed for Android some early on, then Android simulator used QEMU, for example. So you can go download, install, it runs on every platform. Basically, you can model a processor or even model simple systems around that processor. And then tools like Renode and all, in turn, which I mentioned last time, is something which can model the whole system, use QEMU. So QEMU, in some senses, is kind of a powerful open source
processor simulator. Not everyone uses it though, right? I mean, if you're really into very optimized thing, like for example, like when Apple lets you run an x86 binary on their new M series processors, they're not using QEMU, okay? They're using some direct binary translation and all. But for a lot of other stuff, QEMU is very good. Other examples, so like if you develop an app for iPhone, let's say for example, using Xcode, which is Apple's thing, there's a pretty nice iPhone simulator, and it's actually a pretty complete system simulator. So it's not simply modeling the processor, but you actually boot iOS onto the screen. It models sensors, models touch, stuff like that, even models network connectivity, so you can check your app under different network bandwidth, for example, because kind of the idea is sometimes you may want your app to adapt to network connectivity. If the bandwidth is low, maybe your app may behave differently than if the bandwidth was high, as well as model for location and stuff like that. So some of these simulators go far beyond than simply modeling the processors. Okay, so now of course, I mean, with a company like Apple or Google behind, they can make them very rich. For other embedded devices, it's not so, right? I mean, I tried looking, I mean, like occasionally I get pings from companies claiming, yeah, they have a simulator for Arduino and all, but they're far more rough than these kind of things. So, but platform like Renode.io, you could do a fair bit, but nothing as polished. So this is Arduino simulator which I had seen. It works for a particular Arduino. You can plug things to GPIOs and do some stuff. I've seen somewhat more polished version of these things. Also, there was a UCLA startup which had once contacted me, which claimed to, but nothing very polished. Part of the problem is there is no one embedded system, right? I mean, iPhone, there is a handful of these, and even for Android smartphone, it's very hard to create I mean, there's no such thing as a generic embedded system. Okay, so and the challenge is that even the tools that exist, I think we are so used to in this space for freebie tools and all that, it's kind of a bit difficult to monetize. I mean, you can't like education is not that big a market. So most of the stuff that happens, like when people create their emulators and simulators for the particular product they are developing, and it all just remains in-house. So simulators play a big role. Another thing is that when you are working with embedded systems, you are often doing what is referred to as bare metal programming, and kind of what it refers to is that instead of working with an abstract view of the system, which the operating system provides through system calls, essentially a set of APIs, oftentimes here you're much closer to the hardware. You have to, generally speaking, you may need to know about what particular sensor it is, what its capabilities are, and I've sort of made that point earlier on also, which is to fully exploit, you may need to learn about what the processor's features are, and also data sheets are your friend, and one needs to dive lower. Now you may say, okay, but hey, I've programmed on Raspberry Pi and it looks no different than a Linux laptop. True, but then you're not really doing any deep embedded programming. You just happen to run on a tiny Linux computer. And you can certainly do a lot of reasonable stuff with that, but once you go beyond the simple obvious type stuff, you have to become familiar with the hardware. Interrupts, and just generally, I mean, it continues with the theme of bare metal programming. Interrupts play a very important role because embedded systems interact with the outside world, and when they interact with the outside world, then essentially they have to, at some level, they'll have to deal with events of some form, as in something happened, a byte arrived, a sensor captured a sample, and so on and so forth. So interrupts become extremely important and a part of the I/O. So when it comes to I/O, there are a couple of ways you can do I/O, right? I mean, what you can poll, or you can work with this event paradigm. And polling has its disadvantage of like the processor is busy doing things, so interrupts become supremely important, which is essentially a sensor or an actuator waking up the processor to then say, hey, attention is needed. Hopefully all of you have seen interrupts or at least heard of interrupts in some course or the other, but you can't escape that. So deep down then, I'm going to skip this. Everyone knows interrupts, right? Anyone? Okay, so I'm going to skip that. Just one thing, one thing to keep in mind is interrupts. An interrupt handler at some level looks like a function, but it has some key differences, right? I mean, firstly, usually when you get into a interrupt handler and you are writing the code there are a lot of things which you could do in the regular code you can't do in the interrupt handler. In particular, you can't do anything which will cause the processor to wait, right? Because then the whole thing will hang, right? You can't also access a lot of things that the operating system provides. You can't access them inside the interrupt handler. So interrupt handler is like bare bones programming. So you can't open a file, stuff like that, that you sockets, things like that, stuff that you are used to at the user level. So there are things that you can't do inside an handler, and therefore usually when you write a function which is meant to be an interrupt handler, you have to designate it as such, that this is meant to be an interrupt handler. In some cases, like that's how it's done. In other cases, yes, you can write an interrupt handler, but if you do something illegit, super bad things will happen. So interrupt handlers, just one has to be careful. Also, when an interrupt happens, then in most cases you will not have nested interrupts, because if interrupt inside an interrupt, that can be pretty tricky to handle. You also need to become familiar with that how the processor is handling interrupts. So processors differ, but very commonly, like processors may have more than one type of interrupt, high priority, low priority, or multiple levels of priority. So being familiar with those things is often very helpful, although typical things like Arduino and all abstracted away. I'm sure many of you have done Arduino programming, and there you can write an interrupt handler in a very special manner, and so it kind of hides a lot of stuff from you. But if you're doing some more serious stuff, you'll have to know what is happening at that level. Okay, so this brings to this point on if life would be pretty simple if all that was happening was I had one algorithm, one piece of function running on the processor. But then the problem is if I'm to wait for something, then the whole processor has to lie idle. Or so, like for example, if I'm waiting for a network packet to arrive, the whole processor is sitting idle. So it becomes extremely important, this ability to share a piece of hardware among multiple pieces of software. That's what distinguishes software from what we call as hardwired implementation. In a hardwired implementation, if you think of, like, let's say an adder adds two numbers presented at its input, and whenever the input changes, it after some delay will reflect a change in output, but at all time it's just doing addition. Okay, it doesn't if I wanted to do something else, then I have to kind of if I want to do a different addition, I have to just present the new set of inputs out there. So hardwired implementation, you can think of them as a physical device which always does a function, that fixed function, nothing else. Even if you have a sequential logic, it's the same story. I mean, I have a finite state machine with some data path, and takes some imports, does something, but that's all it is doing all the time. What makes software different, when we say something is software, what we really mean is it's a piece of hardware which at different times, given different software, can do different things. Now, if always it did just one particular program, then it's essentially, again, a little bit closer to being just hardware, it's just doing one thing. What makes software really exciting is that even very rapidly I can kind of move back and forth between different pieces of software. So fundamentally it's about how do you multiplex hardware among different pieces of software. Now, so this brings us to this notion of like, what are the different, how do we think of software? Like if you say software in terms of some modules, and those modules are running on the same hardware, what are those modules? So one way of thinking about them is how these modules are organized. So at the leftmost are good old function calls. So I have, like the way I've kind of shown out here, module A is running, and then at some point I pass control to module B runs, then module B finishes, then the control returns back to module A. So there is a strict master-slave kind of a hierarchy out here. There's a caller, there is a callee. When A calls B, then it passes arguments to it. When B returns, it returns the value back to A, and there are conventions that are combination of hardware, but more importantly compiler, on how all of this happens. So like for example, the compiler may say the first argument is always in register R1, the second argument is always in register R2, the return value is in register R3. We have concepts of stack pointer and a stack frame where we kind of store necessary information so that we can get back. Okay. So that's what happens when we call like this. Now, at some level it's great, but here nothing is ever truly running like conceptually. Even it's like A has to call B and B has to return, right? I mean, so there's this rigid hierarchy. On the other extreme, I'm going to skip the middle for the moment, you have threads or processes that I'm sure you must have, I mean, at least you use them all the time, whether you have programmed it on it or is different. So I can think of my overall application as consisting of A and B running in parallel. Maybe A is monitoring a sensor and B is monitoring a radio, and they're conceptually running in parallel. As when I write A, I don't have to worry about B. When I write B, I don't have to worry about A. Okay. But the operating system or the hardware or some combination thereof is going to decide when A runs, when B runs. If I have two processors in my chip, two processor cores, A and B can both run in parallel. If there is a single processor, then maybe I can run A and B alternately for little bits of time. I can schedule them onto the same processor core. But when you are writing the application, A and B to you are concurrent, right? They can run concurrently if given enough hardware, the two can be truly run in parallel. So this is how processes in your operating systems and all are organized, right? I mean, so I write, like when I'm writing two different programs for my computer, I don't have to worry about each other, right? They are conceptually run in parallel. Okay, so and many programming languages give you threads which basically bring it within the program, so it's not just processes, but you can think of your one application to have these constituent parallel constituent modules which conceptually can run in parallel. So like if you like programming in Python, Python has threads, and those threads run concurrently. If given the operating system, they can be truly concurrent if you have sufficient number of processors, and so on and so forth. Okay, so that's threads, and if you've done C++ or whatever, it's much more very routine. There is a middle ground which is far less common. It's called coroutines. So left one is subroutine or functions, right one is threads, middle one is called coroutines. And the idea in coroutine is the following. So A can call B, but B can call A. So they are kind of sitting that they are equal to each other in that regard. So the difference is the following. In the subroutine, whenever A calls B, B has to finish and then we return to A. Next time A calls B, again we will start from the very beginning of B. Okay, we always enter B at the top. But in coroutines, what happens is, if you see out here, A called B, first time it entered at the top, but then when we return, then A starts, but next time when A calls B again, it's called resume in this case, to resume B, then we start B where we left off, as opposed to from the very beginning. So clearly we had to remember where we exited B last time and then enter back from there, right? I mean, whereas in subroutine, I don't need to remember anything about B, right? I mean, every time I just start from the top. Okay, I don't have to remember where I exited from B. Whereas here I have to remember where I exited from B so that I can resume from there, and likewise. So they are kind of coroutine, they are symmetrical but sequential. So that's a very important point. Here, if you gave me two processors, I can run both of them truly in parallel. Here, at any given point in time, either A is running or B is running. Okay, even if you give me two processors, I can run them in parallel. And certainly not here, right? Subroutine is strictly sequential. So this is sequential, but it has this flavor of things running kind of in parallel. Okay, because I can write the two as if logically they are doing in parallel, they are equivalent to each other. So some programming languages have this, and in other programming languages they may not have it, but then they provide it as a package to you, so like as a coroutine package. One programming language, actually let me ask, anyone knows of a programming language which has coroutines in it?
Python.
Huh? Python? Not built in. Huh? C#. I don't know actually. So you name one language I don't know anything about. But Go. Anyone heard of Go? Go is a language which came from Google. It's actually created by the same people who created C. The labs of the same crowd. Go has coroutines in it. Okay. And then for Python and C and C++, we have packages that provide. Okay. So subroutine, threads, and coroutine kind of fits the sweet spot in the middle. Okay, so three types of packages then, and then in terms of like one way of thinking about it, how complex is it to implement these things? Well, if you are at the right hand side, then let's say we were running these threads on the same processor, a single processor, single piece of hardware, then the OS, if it were to juggle between these two, it will have to remember the state and all, right? I mean, every time it stops thread A and switches to thread B, or stops thread B and thread A, it has to store that state someplace. So that's one thing. Secondly, these different threads are logically running in parallel, which means I have two program counters, right? I have to at all point in time know where thread A is, where thread B is. They will have their own stacks. So all of that needs to be done. Whereas the first two solutions, they are sequential. That means I can run them on a single stack. I don't single program counter, single stack. So this is something to keep in mind. So complexity wise, the right hand just is more complicated to implement, and certainly more memory hungry to implement. You have to upfront decide how to divvy up, like if I have a certain amount of memory, I have to allocate stacks for each one of the thread, for example. Okay, whereas I can get away with a single stack in the other two. So just complexity kind of goes up. You will need sort of a runtime and a scheduler, and which is juggling
between things. If in the rare case that you have as many processors as threads, then of course life is simple. You just map a thread to a processor and let it run all the time. But generally, that's not the case, and it will kind of defeat the purpose. So, okay, so that leads to kind of a very key thing about, I guess, software broadly, obviously, particularly at lower layers, but certainly with embedded systems, which is how do we organize the software? I mean, we see these kind of modules. So it kind of boils down to really two very important concepts that one has to deal with, which is at the heart of these things. One, so embedded. If you think about the software at the heart of an embedded system, it has to deal with events, namely it has to interact with what is happening in the outside world and potentially happening asynchronously, right? Out of the blue, a sensor may say, hey, I need attention, right? Okay, so this is, if the world was totally prescribed and we knew when something will happen, then life would be very easy. So events are these asynchronous things which are happening, which may require some processing done when the event happens. And the other thing is concurrency, that is, things happen simultaneously. So these events may happen in some order which we don't know, and they may happen simultaneously, and I may have to deal with them. A sensor sample arrived, or whatever, a batch of sensor samples arrived, and I'm doing an FFT on them, and in the middle of it, a packet comes over the network, and I have to deal with all of these things. So foundationally, then, we have to worry about how to deal with these things. Okay, so events arriving at arbitrary times in unknown orders and potentially in parallel, and then how do you have your software deal with these things? So organizing the software to do this is really kind of leads to some of the common ways that you see. So very loosely speaking, you would see that embedded software systems, their core are really organized around one of these two approaches. They are either multi-threaded or they are event-driven. Okay, and sometimes the boundary is not that clear, and you can certainly implement one on top of the other, but that's kind of the idea. So some systems you would see that they provide you multi-threading, that is, you can write software modules which are written independently, and then the underlying software provides a kernel which takes care of the responsibility of juggling the processor between these different threads. And depending upon what the events are happening, when they are happening and all, a thread may run, be stopped, resumed, so on and so forth. And of course, these threads on occasion have to interact with each other. One thread may send a message to another thread. So the richer or more complicated systems